Here's a fluid mechanics question which actually combines several principles, and it's mostly hydrostatics, and it's the type of question that you might see as a first year undergraduate who is doing some kind of engineering, or you might even see this as a high school student preparing for something like an Olympiad exam. So if you'd like to see anything similar to this on the channel, let me know in the comments. So let's see what we have to do. There's a lot of text, but we'll try to simplify this as much as we can. So basically, we're dealing with a cylinder which has a certain radius r. So basically the distance from the center to the edge is lowercase r, and then the length of the cylinder is given by lowercase l, like this. And we know that at the halfway point, the cylinder has a thin tube which is upwards, and inside the cylinder there is a spring. Now the spring has a spring constant given by 400 pi newtons per meter, and it also has a relaxed length of L0, which is 15 centimeters. And there is some water in this or on one side of the piston there is water, and that water compresses the spring, and it's also raised above the top edge of the cylinder by a certain amount h, which we don't know how much that is, and that's what we're trying to find. Okay, so the other important thing to note is that on this side of the cylinder there's a small orifice, which means that the pressure inside this compartment is the same as the atmospheric pressure. So that's the question's way of saying that we don't actually have to worry about atmospheric pressure because it's acting everywhere. Okay, so we'll just deal with gauge pressure. Now, to do this, what I would first do is redraw the cylinder. So we have, first I'll draw the cylinder like this, and then I'll draw the tube. So the tube is at the halfway point, which is somewhere around here like this. So let's do that. Let's draw the tube going upwards like this. Okay, and the water goes up to some level h compared to to the upper surface of the cylinder, and then we have water inside, and then we have a piston which is being compressed. So the piston is sitting somewhere here like that, and yeah, so the spring is compressed like that. Okay, so let's try to think about what's going on here. Underneath the cylinder there is a fulcrum point, okay, and everything is in balance. So what we know is that the piston has a mass, and obviously the water inside the cylinder has a mass as well, and we know that everything is now in equilibrium. Okay, so in other words, the moment that's trying to rotate the cylinder one way is balanced by another moment trying to rotate the cylinder the other way. So there are two moments here that are acting. The first one is due to the weight of the piston, which is acting here, right? So the weight of the piston is mg, where m is the mass of the piston. And in addition to that, the water has its own mass, which is which has essentially the weight mg, okay, associated to it. Now here's something that is worth noting. Those are the only two forces which are producing moments about this fulcrum point that let's call O. okay? Which means that if the moment caused by the red force is equal to the moment created by the blue force, it means that because those two forces are equal to each other, because what we know is that the mass of the water, it says here, the mass of the water equals the mass of the piston. So because the two moments are the same and because the two forces are the same, it means the two moment arms are the same as well. So in other words, if we draw this a bit better, what we will end up with is the water weight is acting at a certain distance from the fulcrum, which is the same as the distance of the piston weight from the fulcrum. Okay, so those two distances are the same essentially, and we have to think of a way of finding what those distances actually are. Okay, so let's try doing it this way. So I'll just draw the bottom part of the cylinder just to make things a bit simpler. Right, now this has an overall length of 33 centimeters. So this is going to be 33, well, let's actually use SI units. So let's use 0.33 meters. Right, now at the halfway point, we have the fulcrum, right? We have where the cylinder is essentially sitting, where it's touching the ground at just one point. So obviously this distance is half of 0.33, so that's 0. It should be 165 meters. Okay, so in addition to that, we know that, let me actually draw this side as well. So this half is also 0.165. Now the piston has a relaxed length of 15 centimeters, which means that the distance from here to, let's say, maybe somewhere around here marks the relaxed spring length. So that's 0.15 meters, and those are meters as well. So that's where the piston, that's where the spring would be if there's no water in the cylinder. But in our case, we know that the piston is not actually here. Instead, it's, let's say, somewhere here. Okay, we don't know exactly where, which is why I'm going to call this length, let's say we can call this L prime. Okay, this is the final length of the spring when it's being compressed by the water. And that is pretty much everything we have. So we will try to figure out a way of writing the moment due to the piston, as well as the moment due to the water. So all we have to write is an expression for this length as well as an expression for this length right here. Right, so let's start maybe with this one. So let's try to figure out where the center of mass of the water is actually located. Okay, so here's what we have. The water is spanning from the left side of the cylinder all the way to basically here, because this is where the piston is, remember, right? So if the water spans from the left side all the way to where the piston is, it means the center of mass is in the middle, right? Because the water is distributed uniformly. So whatever this length is, the center of mass is going to be at the halfway point, which I'm just going to draw it here. So we have to figure out where exactly that is. Right. So let's figure out this length that we call x. So to find x, we can simply write that x plus L prime is equal to 0.33, like this, which means that x is therefore 0.33 minus L prime. Okay, so the center of mass of the water is at a distance at half of that basically away from the left-hand side, which is essentially 0.33 minus L prime divided by 2. Now, what we actually have to find, remember, is the distance from the fulcrum, from point O, to where this center of mass of the water is. In other words, we're trying to find this distance. Okay, so that distance can easily be found by subtracting this from 0.165 meters. Okay, so let's actually do that. We have this distance, let's call this D1. So D1 is 0.165, and then we subtract 0.33 minus L prime over 2. Right, that's it. So we're gonna leave this as it is for now because we don't know what L prime is, but we need another equation to be able to find it. And to do that, we're gonna find an expression for, if we go back here, we're gonna find an expression now for this distance. That's the distance from the fulcrum to the piston, okay? So let's see how we do that. If you look at this diagram, you should realize that it should be relatively straightforward. So we're trying to now find this distance that we call D2, which remember is the same as D1 in magnitude. So we can write, let's write here that D2 is simply equal to 0.165 minus L prime. Right, that's all there is to it. So we have half of the tube, that is from O all the way to here to the right hand side, is 0.165, and then we subtract L prime and we get that D2, which is what we're looking for. So that's it. It's simpler than working out D1. So now what we have to do is we use the fact that D1 and D2 are equal to each other, so we're going to equate the two expressions and find what L prime is. So let's write that here. So we have 0.165, and then we have minus 0.33 minus L prime over 2. Right, so this equals this, which is 0.165 minus L prime. So if we move things around, well, first of all, you should see that those cancel out. And then we essentially have 0.33 minus L prime is equal to, well, 2L prime. So 3L prime is equal to 0.33. So finally, L prime is 0.11 meters. So this is the final length of the piston, or of the spring, basically. So in the final state, when there's water inside, this distance is 0.11 meters. Okay, so it started with relaxed length as 0.15, and therefore the change in length was 0.04 meters. So this is how much the spring has contracted due to the water. So now that we found this, let's actually talk about the water itself and what it's actually doing on the piston and then on the spring. So this is a hydrostatics problem simply because this water is not going anywhere, right? Which means that this piston is experiencing a force due to the water pressure, and that force is pushing this way, okay? And to actually find this, well, technically there is a more precise way of doing it by doing some integration or finding the area under the graph, but we're gonna do this in a more simplified way. So what I'll do here is I'll draw the piston and a bit of the spring, and all I'm gonna say is that the entire pressure is going to act at the halfway point. Okay, and that pressure is going to be equal to rho g times the depth. Okay, so the depth, we're measuring it from the very top, that's where the free surface is. and we're going all the way to the halfway point. So we're looking at this distance, which is h plus the radius of the cylinder, which is r. So this is h plus r. That's the pressure. And to find the force, we just multiply this by the area. So it's the pressure like this, and we multiply this by the area of the piston, which is pi r squared. Okay, so that's the force due to the water, basically. And this is being balanced by the force due to the spring, which is K times delta L, right? So it's the spring constant multiplied by the change in length. So now if we equate those two things together, we should get an expression for what we're looking for, which is H. That's the only thing we don't know. So we have rho G times H plus R times pi r squared. This is equal to K times delta L. So let's actually try to put the numbers in. We have 1,000 for the water density. For G, I'll use 9.81, and then we have H that we don't know. R is given as 10 centimeters, so that would be 0.1 meters. And then we have pi, and then we have 0.1 again, and then squared. Right, and now K is the spring constant, so that's 400 pi multiplied by the change in length of the spring, which is what we've been doing here, basically. So all this thing that we did here with the diagram and everything, we did it to find this value of how much the spring has been contracted, basically. So that's 0.04. Now, you might notice the pi's cancel out, which is good. So at this point, it's just doing this on the calculator and see what we actually get. So let's see what else we can do to simplify things. So this here is 0.01, which cancels out with this, and we get just 4 on this side. So if we rewrite this, we get 9810 and then times H plus 0.1 equals, and this is going to be 1600, like this. And then we have H plus 0.1 equals, and now we have to use a calculator. So that is 0.163. And then if we do this final subtraction, this is going to become 0.063 meters. Or we can say that this is 6.3 centimeters. So in other words, we found how much the water raises above the level of the cylinder. So this amount, H, is 6.3 centimeters. Okay, so just to quickly recap, because there were quite a few steps going on. The first thing we did was we looked at a balance of moments, and we did that to find how much the spring has changed in length, and we found that here. And then we used the water pressure, which is acting on the piston, and that is equal to the spring force, and then we use that to finally find out what H is. And that's the end of the question.